In this video, I'm going to go over binomial probability distributions. A binomial experiment is a type of probability experiment where there are exactly two possible outcomes for each trial of the experiment. The word binomial, the root bi, means two, and there are two possible outcomes. We usually call these two outcomes success and failure, denoted by S and F, though these two possible outcomes can be anything, like heads and tails, or drawing a red card from a deck versus a black card, or liking chocolate ice cream better than vanilla ice cream. But we do say that one of them is a success and one of them is a failure in order for the equations to work out. Also, for something to be a binomial experiment, there has to be a set number of trials, and each trial has to be independent from all of the other ones. So the outcome of one trial cannot affect the outcome of another one. The probability of success, P of S, is the same in every trial, and also we use the random variable R to represent the number of successful trials in our probability experiment. A very simple example would be flipping a coin 10 times. We can say that success is heads and failure is tails, but you could also say the other way around, that failure is heads and success is tails, as long as you're consistent once you decide which one is success and which is failure. This is a binomial experiment. There are two outcomes. Each flip of a coin does not affect the outcomes of the other coin flips. There's a set number of times that we flip a coin. We flip it 10 times, and the probability of success does not change at all. So this is a binomial experiment because it fits all of the criteria for being one. Another example. A medical procedure has a 99% chance of success. A doctor is to perform this procedure 192 times. So far, we have success versus failure, and we have a set number of times the doctor is going to perform this procedure. In theory, the outcome of one trial or of one surgery doesn't affect the outcome of the other surgeries. I know that in practice, maybe there could be some impact. In the real world, it's always a little more complicated than just, straightforward, oh, it's always exactly 99% chance. But it's going to be close enough that we're going to call this a binomial experiment. Something that's not a binomial experiment would be drawing 10 cards from a deck, and we're going to say success is getting a face card and failure is not getting a face card. The reason this is not binomial, even though we have a success and failure, we have two outcomes, is that every time you draw a card, you skew the number of face cards versus non-face cards in the deck. I'm assuming you take the card out and don't put it back. So the outcome of one trial is going to affect the next one. If you draw a face card the first time, then the second time you have a slightly decreased chance of getting a face card. So even though there are two outcomes, even though we can say something success and failure, we have this problem where the trials interact with each other, and therefore it's not binomial. Some notation that we'll use for binomial experiments. We'll use n to denote the number of trials. So in the previous examples, I flipped a coin 10 times, n was 10. The doctor performed a procedure 192 times, so n was 192. P of S denotes the probability of success. Lowercase p is another way to write probability of success. We're going to use it to mean the exact same thing. It's just a little easier to write. Same thing with P of F, probability of failure. We have a shorthand for that, which is just lowercase q. And last, we've already mentioned this, but R is the number of successes that we have over our n trials. So let's do an example of a binomial experiment with these variables. We have 8 decks of cards, and we're going to pick a card from a deck, and success is getting a heart and failure is getting anything that's not a heart. Because these are 8 separate decks of cards, then it doesn't matter what we draw from the first deck, it's not going to impact the second card we draw, which we'll take from the second deck. So because these won't interact with each other, because the probability of one will not impact the probability of the next one, and the probability of success remains constant for all 8 decks, then this is a binomial experiment. And let's say, you happen to get hearts, hearts, clubs, spades, hearts, diamonds, clubs, clubs from our 8 decks. Then n is 8. R is 3 because we got hearts 3 times out of those 8. And then the probability of success is 1/4 because the hearts cards make up 1/4 of the deck. And the probability of failure, which is Q, is 3/4. So we can apply these values if we are using the binomial probability formula. And this is a formula that tells us the probability of getting exactly R successes and N trials. So our formula is N choose R. You might have seen this as N, like a little n, capital C, little r, but this is another way of writing N choose R, times the probability of success to the R times the probability of failure to the N minus R. So we will apply this, and the remainder of the examples, the next 2 examples, are either exactly quoted from or largely based off of examples from this book that I have credited here. First example, knee surgery. Microfracture knee surgery has a 75% chance of success on patients with degenerative knees. This surgery is performed on 3 patients. We want to find the probability that the surgery is successful on exactly 2 of those 3 patients. So what we do is we apply our formula. First, we identify what the different variables are. N is 3 because we're not performing the surgery. Somebody is performing the surgery 3 times. P, the probability of success, is 3/4 or 75%, making Q, the probability of failure, 1/4 or 25%. And R, the number of successful surgeries, we want to calculate the probability of 2 successful surgeries, so R is 2. Then, the probability of 2 successful surgeries is, we start with 3 choose 2, so that's 3 factorial over 3 minus 2 factorial times 2 factorial, times, and then we have the probability of success to the R power, 75%, to the second power, and then times the probability of failure, which is 1/4, to the N minus R power. So N is 3, R is 2, so 3 minus 2 is 1, and that's why I have an exponent of 1. So 3 choose 2 evaluates just to 3. 3/4 squared becomes 9/16, and 1/4 to the first power is 1/4. If you calculate that out, eventually you get down to 0.422 approximately, which means that there's approximately a 42% chance that there will be exactly 2 successful surgeries. The next example, I changed this slightly from the example in the book. So in a survey, 56% of people said they like beef better than chicken. 7 adults who participated in the survey are randomly selected, and these 7 adults are asked if they like beef better than chicken. What is the probability that just one of these 7 adults prefers beef? That would be R equals 1. I have defined liking beef better to be a success and liking chicken better to be a failure. That is my own preferences being superimposed on this problem. You could define it differently. What is the probability that just one prefers beef? That's going to correspond to R equals 1 because I am saying that liking beef is a success. What's the probability of exactly 2 preferring beef over chicken? And so on. We're going to find the probability of exactly 3, 4, 5, all the way up through 7. And to do this, we construct a full probability distribution where we compute this for every possible value of R. So realistically, we want to start with the probability that none of them like beef. And so that is probability of 0 is 7 choose 0 times 0.56 because 56% like beef to the 0 power because we're assuming this is the case where none of them like beef times 0.44, which is the leftover probability of people who prefer chicken, to the 7th power. And if you look down these columns, the first time you see 0.56 raised to a power, it's to the 0th power, then it goes to the 1st power, 2nd power, 3rd, 4th, 5th, 6th, and 7th. So you don't have to necessarily figure out what the exponents are every time. Just know that P of 0 versus P of 1 versus P of 2, the exponent is going to just step up 1 every time on the successes. So if you compute these out, we get our binomial coefficients, which are 7 choose 0, 7 choose 1, 7 choose 2, and so on. and I put those in first. So 7 choose 0 is 1, 7 choose 1 is 7, 7 choose 2 is 21, 35, 35, 21, 7, 1. So those numbers are coming just from calculating 7 choose whatever. And then I left the rest the same and then computed those out, and we got that the probability that none of them like beef is 0.0032. So that's 0.32%. And then the probability that exactly one likes beef is 2.84%. Probability that two of them like beef is 10.86%. So this is a lot of computation, and one way that we can make this easier is if you know Pascal's triangle. It's really nice because Pascal's triangle does have the binomial coefficients as each row of the triangle. So if you know this triangle and you know how to construct it, what you can see is that the bottom row is 1, 7, 21, 35, 35, 21, 7, 1. And you can see in my calculations over on the left-hand side of the screen that the choose coefficients that I calculated are the same exact things. Pascal's triangle can make this a little bit easier. That's a little bit of a shortcut, but that is our probability distribution that tells us the probabilities of every possible scenario corresponding to every value of R in this example of people liking chicken versus beef. That is it for this introduction to binomial probability distributions. I will see you next time.